Hello everyone, I'm Dian Wang from Northeastern University. I'm very glad to present to you our work, a general theory of correct, incorrect, and extrinsic equivariance. Recently, there has been a lot of success in using equivariant neural networks in various domains. By enforcing the problem symmetry in an equivariant neural network, we can greatly improve the sample efficiency and generalization of training. However, the existing works typically assume that the model symmetry perfectly matches the problem symmetry, while real-world problems can easily violate such an assumption. For example, the problem could be partially symmetric. There might be some symmetry breaking factors, or the data could be noisy. In those imperfect scenarios, what will happen if we stick to an equivariant model is underexplored. For example, imagine that we are solving the MNIST digit classification task using an equivariant network that is invariant to pi rotation. For a subset of digits, a pi rotation will not change the digit, and the model symmetry agrees with those data. We call this scenario correct equivariance. For 6 and 9, a pi rotation will change the digit, meaning that the model symmetry conflicts with the data. We call it incorrect equivariance. For other digits 3, 4, and 7, a pi-rotated image is not a digit, meaning that the model symmetry transforms the data out of distribution. We call this scenario extrinsic equivariance. Moreover, different group transformations can also lead to different results. Consider digit 2 and 3 with vertical flip transformation, which will turn a 2 into a 5 while keeping 3 unchanged. If our network is invariant to both pi rotation and vertical flip, we will have a mixture of equivariant types for both different data and different group elements. Since real-world datasets with symmetry often include some imperfect symmetry in such a form of mixed correct, incorrect, and extrinsic equivariance, it is important to quantify the error this will create for an equivariant neural network. Let's consider lower bound in our example of using D2 invariant network for the MNIST classification. For an image of digit 2, its orbit would be 4 transformed images with respect to the group D2. Out of the 4 transformations, 2 will give us correct equivariance, and 2 will give us incorrect equivariance. Let's imagine that the probability densities for the 4 images are the same. Then, the majority label, which is the label associated with the most data of the orbit, would be 2. The optimal solution for the invariant network is to converge to the majority label, and it will make a wrong prediction on the data with a different label. In this case, the error rate will be 1/2. We call the error k of the orbit gx. Now, doing the same operation for all digits, we can calculate a lower bound as 1/10. Formally, we define the total descent for an orbit as the integrated probability density of the elements that has a different label than the majority label. Then, the lower bound for classification error rate can be calculated by taking the integral of the total descent over the fundamental domain F. We also calculate the error bound for invariant and equivariant regression. Please see them in the paper. Lastly, we discussed the potential harm of extrinsic equivariance. Our prior work demonstrated that the potential benefit of extrinsic equivariance, but we showed that it can also be harmful. Consider a binary classification task where the input domain is in R3. The data distribution is 2 spirals on 2 separate z-planes. If we use a z-invariant network, it is effectively the same as collapsing those 2 spirals into the same plane. Notice that this is still extrinsic equivariance instead of incorrect equivariance because the 2 spirals don't overlap. For a standard network, the decision boundary could simply be an S-like plane. However, for a z-invariant network, the decision boundary is much more challenging to generate, making the symmetry in the model harmful. To sum up, in this paper, we define a mixture of equivariant types. We further demonstrate the theoretical lower bounds when there are incorrect equivariance in a dataset, and we show that the potential harm of extrinsic equivariance. We perform a number of experiments to verify our theoretical analysis. Please see them in the paper. The major limitation of our work is that calculating the bounds requires the probability density function of the domain, which could be too strong of an assumption of the dataset. Moreover, we only have a partial understanding of when extrinsic equivariance is helpful or harmful. Quantitatively analyzing the effect of extrinsic equivariance would be an important future direction. Thank you.